Now that we've sorted out the area design with SBC, let's explore how OSPF can interact with BGP near the internet edge. Currently, SBC is using an active standby for internet connectivity as we saw previously, but they're having congestion issues on their primary link. They're wanting to do some kind of active-active approach, but in an unequal way. They've got 3 networks over the internet that they're hosting cloud apps in, and they have a combination of CAD systems, team chat collaboration apps, and file transfer email stuff. For the time-sensitive apps, like the CAD systems and the chat, they want to use the primary link, but for all the non-transactional stuff like file and email, they want to use the backup link. The solution should provide automatic failure. If one of the links fails, then all the traffic should be moved to the other link. This is a fairly common internet edge scenario, but we're not going to do any BGP manipulations to make it work. We're only going to solve it with OSPF. In our particular case, our ISP, which is R19, is not sending a default route. It's actually sending our 3 individual prefixes down. One useful technique we can do to scale OSPF and keep the routing table smaller is to conditionally originate a default route when certain prefixes exist in BGP. Basically, these are routes of interest, and if any of them exist, we can originate a default route. Let's start off by originating the same default route in terms of type and cost from both R6 and R7. The benefits of conditional origination is that we don't always originate a default, which can avoid any black holing issues, and it also avoids any risky redistribution from BGP into OSPF. Let's quickly explore how to do that conditional advertisement on the command line. I'm starting off on R6, and I'm showing the relevant configuration items. First, we have a prefix list that's going to match the routes of interest, and if any of these are present in the routing table, then OSPF will originate a default route. We need to reference that prefix list inside of our route map because ultimately the route map is going to be applied into OSPF. We apply the route map to the end of the default originate command where we specify the different characteristics of the default route, and the route map just gives us the ability to do that conditionally. We can confirm that the default route is being originated right now using the OSPF database command shown. We know this is the default route because the link state ID is all zeros, and the advertising router is our local router ID. We can also see that it's a type 2 external by default, which is expected, and the metric is set to 10, which is consistent with our configuration earlier. Pretty soon, we'll see how this impacts our traffic flows. If we do that configuration, we're going to have this weird load balancing scenario. Because both routes have the same seed cost and they're using E2, we're going to have a generally symmetric topology. This is going to use both links at the same time, and while it does give us active-active with automatic failover, it doesn't separate our apps into time-sensitive versus not, so it's not really adequate. Let's quickly confirm that by going to the command line and doing some quick trace routes. Let's use traceroute on R3 to trace the path to the internet. I'm going to send extra traceroute probes so you can see the problem. If you look closely, you can see that we are doing equal cost multipath or ECMP across both R1 and R2 for the first hop. At the second hop, depending on whether it went to R1 or R2, we then use R6 and R7. Last, you can see the traffic always makes it up to the internet, but sometimes we use our slow backup link. This is the expected result of our configuration above, but it generally doesn't meet our business requirements. So using similar defaults on R6 and R7 was definitely a bad idea, so let's back that out. We want R6 to be generally preferred, meaning we should use R6 by default and then maybe have some specific exceptions that go through R7. We can use OSPF Type 2 externals for this, which I believe makes sense when you have these cold potato scenarios. We want to forcibly choose R6 for most traffic with some exceptions through R7, so we don't need to evaluate the entire OSPF path, which would make E1 a poor choice. Of course, you could use E1 on R6 because it's always preferred over E2, but in my opinion, that's kind of a poor scale solution because you can only have 2 egress points when you do that. We could use E1 on both devices at the same time. It's a poor choice for active standby, but for active-active when you have specific prefixes that need to go a specific way, it's really not great for that either. Let's head to the command line and try to implement these Type 2 externals and verify that it works. Let's make a small change on R7 by updating the metric to 20. Because we're using Type 2 externals, This means that all the routers should always prefer R6 for their egress traffic outside of OSPF. This is actually what we had earlier for the first module, we just snapped it back in. Let's confirm that R7 is originating a default route with the new metric using the OSPF database command shown. The LSA looks almost identical to the one we saw on R6 because it's still a default route, but the difference is that it's originated by R7 and has a metric of 20. R3 should have both of these LSAs, so let's compare them from Area 1's perspective. To do this, we can look at the OSPF database for the external route and only include a few key fields. That will cut down on the output and allow us to perform a simple comparison. As expected, the default route from R6 has a seed metric of 10, while the one from R7 has a seed metric of 20. If we check the routing table, only the one from R6 should be installed. We can see it says from 10.0.0.6, which is correct. We're slowly getting closer to a solution here. We have our time-sensitive apps going through R6, which is correct, but we also have our non-time-sensitive apps using R6 as well. This is the initial situation we found ourselves in, and we've just gotten back there using some different techniques. The reason R6 is always chosen is because its E2 seed cost is always going to be 10 versus R7, which is always 20, and we always pick the lower cost. If R7 ever ends up in the transit path though, we might end up with interceptions because R7 is going to prefer its eBGP path to R19, so as long as R6 is in the path, we should be okay. Before we move on, let's verify that we're actually seeing this in the network on the command line. In the previous demo, we confirmed that the routing was correct, but now let's test the traffic using traceroute up to the internet. Okay, that path looks correct, and we're no longer doing any ECMP, which is exactly what we want. Let's also test the path to 203.0.113.19, which is our file sharing application network. Ideally, we want this to go through R7, but we really haven't set that up yet. Unfortunately, it's using R6 right now, and it might be eating up all of our bandwidth on that link. Let's figure out how to fix this. Probably the easiest way in order to achieve our scenario completely is to leak longer matches using R7. That means we can match the 203 network and redistribute it from BGP into OSPF. It doesn't matter what the type and cost of that route are going to be because we're going to have that longer match and all traffic towards that destination is going to be attracted towards R7. By using this approach, we avoided a lot of complex BGP manipulations. We didn't change local pref. We didn't do a bunch of BGP policy filtering. We didn't need that. We didn't need to do any hardcore OSPF policy either. We don't need a complex route map. We don't need a bunch of static routes, nothing like that. It's just a simple couple lines of config redistribution, and it completely satisfies our scenario. Let's head to the command line to verify that everything is working the way we expect. We need to make some updates on R7. R7 uses the same conditional default advertisement that R6 does, but it has some additional config as well. We need to specify which routes do we want to leak from BGP into OSPF, and in this case we only have one. We need to wrap that inside of a route map so we can apply it to the proper OSPF configuration. In our case, we're actually redistributing from BGP into OSPF. This can be a dangerous action, but in our case we're being very controlled about it and we're only leaking one route to do a little bit of traffic engineering. Keep in mind that the metric type and metric are irrelevant because the longest match route is going to win and it will never compete with the defaults. Let's quickly confirm that R7 is originating this new route using the OSPF database command shown. We can see the link state ID and the network mask identify the prefix, which is correct. It was originated by R7, and again, we don't care about the metric or the metric type. Once the other routers in OSPF learn this route, we should have access to this prefix across R7. Let's quickly review the solution that we just completed. At this point, we have 3 external routes, all of which are external type 2. We have a default from R6 with a cost of 10, and a backup default from R7 with a cost of 20. This will attract all of our default traffic towards R6. However, we also leaked a more specific 203 network on R7 for our non-time sensitive traffic, which means that traffic will use R7 primarily. In terms of ingress, I'm using NAT at these 2 internet edge routers, which guarantees symmetry, so that's not really an OSPF feature, but it is commonly used. There are other ways to do this with BGP, but again, I don't want to go down those rabbit holes right now. It's not super relevant to dealing with OSPF. Our solution is overall pretty good. It's optimal and resilient in that we can use both routers for both prefixes if there's a failure. We use R7 primarily for the 203 network, with R6 for all other destinations. The default from R6 will cover the 203 network if R7 fails, and the R7 default will cover everything if R6 fails. So at this point, we've satisfied all the constraints and we have a pretty good solution. Let's take one more look at the command line before we wrap up so you can see how all the pieces fit together. If you check any of the routers inside of the OSPF domain, right now you should see 3 external routes. The first 2 are the default routes originated by R6 and R7, and we explored those in a previous demo. You can tell by the link state age that we have a newer route, which is 203.0.113.0. This is another Type 5 LSA, but it is only originated by R7, and it gives us direct access to that prefix across the backup link. Let's check the routing table to ensure we have this installed. We can see it was originated by R7, and the next hop is R2 and not R1, which looks correct. Let's use traceroute to confirm that the traffic is taking the proper path. That's much better. Now we use R7 for egress. It's always a good idea to make sure we didn't introduce any regressions, so let's traceroute to 192.0.2.19 again to make sure it still takes R6. That looks great to me. Now we have traffic using both paths at the same time for specific prefixes. Keep in mind we did this without any BGP modifications, so this is an easy way to do simple traffic engineering in your network without going crazy with BGP parameters. In the next module, we'll talk about scaling and how you can use OSPF effectively in hub-spoke networks.